Okay, thanks very much, and thanks for the invitation. As Joyce says, I was when I came last, it was the weather was so bad that actually the talk was postponed for a day. So it's which I think is unusual. Okay, so this just testing my screen working. So this talk it's based on work that I've been doing for a number of years now, and it's a joint work with a number of people. And I'll introduce the papers that it's based on. And in fact, it's kind of based on some work that's already happened, but there are some ongoing things as we go on. So I'll also introduce some of the people who are working on it. So it's the title is Modeling Evolution in Structured Populations Involving Multiplayer Interactions, and what we're going to be looking at is an evolutionary model on a population that's not well mixed, so individuals that interact with each other. So there's a potentially large population. But some of these will be actually quite small, and individuals interact, but not in a uniform way. So I'll interact more with some individuals than others potentially. And the games that will be played won't all be pairwise games. And this is ongoing project that's been running for a while. So so the first paper is in 2012 with Jan Richter, where we introduced the general idea, and then various people have been involved since. So Karen Patney is one of the people who worked when as a PhD student with as mine a few years ago. And it's currently, I'm still doing a little bit of work with him, but he's now working up a postdoctoral position in Liverpool. More recently, Jan's colleague Igor Iravenko, who some of you will know, has also been developing work on this. And so some of the recent work was to do with Igor. Other people also said Pedro Schmidt from Brazil, but I'm not going to say anything much about Pedro's work in particular here. But he's been involved, and so there are a few other people, and they're current PhD students as well. And this is involved with a couple of European grants. So the earlier one, which is finished, which is a network and involved a number of people on both sides of the Atlantic, which was based on travel. And so that was me going to North Carolina and so on. And in a slightly different projects, people like Ross Cressman were involved, for instance. The latest grant is a training network grant involving lots of people in Europe and PhD students, and that's involving in particular, I've got one of the PhD students is one of the people on this grant. So firstly, I'll say a little bit about both evolutionary game theory and evolutionary graph theory. So what's an evolutionary game? So firstly, an evolutionary game involves typically a typical game involves players. So some number of players, often there are two, and you can sort of say player one, player two. Everyone knows about games, and so similarly, players play strategies against each other, and after you select your strategy, which might be a pure strategy or a mixed strategy, then payoffs follow. So each player will get a reward. And so that's what you have in a typical standard game. For an evolutionary game, you also will have a population of individuals. So the players in any particular instance will be a subset of the population, and that population will actually evolve. It will change in time following an evolutionary dynamics. And so this is the standard kind of idea within an evolutionary game. A classical evolutionary game will be, the usual game will be, population will be infinite, well-mixed population, every individual equally likely to interact with every other. Games played against, so games are played against either everybody, or more usually against random opponents. So your payoff will be some expectation, and then following some dynamics, often like the replicator dynamics, payoffs would increase. So strategies with higher payoffs will increase in proportion, and strategies with lower payoffs will decrease in proportion. And so you're looking for stable rest points of the dynamics, or what's called an evolutionarily stable strategy. This is not formally following the dynamics. It's closely related to, but slightly different. Where it's a sort of static idea where you think of a population following a particular strategy and seeing if you can disturb that strategy by invasion of an invading mutant, and we'll be following that idea in spirit in the way that our populations work. So typically infinite populations, but there's also finite population versions of these models as well. Evolutionary graph theory develops these finite populations and considers graph structure. So not only do I have a finite population of individuals to interact with, but I'm more likely to interact with some than others. And the usual expression is, so you've got a graph of connections. So the vertices are the individuals, or rather the places that the individuals reside. Different individuals replace others at certain times, and there are edges between them, and I can only interact with individuals that are connected by an edge. And I might have weighted edges where the weights are bigger for some than others, and I'm more likely to interact with them. But in the simplest case, you just have an edge, and either you interact with an individual or not. And you introduce a population. So there are two different types, is the usual thought. But there might be many types, but usually everyone is a resident. You introduce a single mutant, and that population then evolves through time in a manner that I'm going to describe. And mutations are sufficiently rare that contest is decided between residents and mutants. So either you end up with all residents or all mutants before a next mutant comes. And so you only have two types in this classical idea. And pairs of individuals interact. So they play games potentially. So sometimes you have fixed fitness cases where I just have a fitness, and then the structure is still important. The dynamics can be important. But pairs of individuals tend to interact, and they play a game against each other. And it might be the simplest possible game, so that I'm a resident, you're a mutant, therefore there's a particular payoff when we interact. And so a typical 2x2 payoff matrix indicates what the resident gets, what the mutant gets. So A is mutant versus mutant, B mutant versus resident, C resident versus mutant, and D resident versus resident. So that's the standard kind of idea. So what you do, you start with a vertex that's selected, and then usually uniformly at random, but there are alternative versions based upon how replacements happen. But the standard model is uniformly at random, and you take that resident away and you put a mutant in its place. And then at each time step, you follow some dynamics. Now, one dynamics is called the invasion process, this is an alternative way alternative name is the birth process. So birth happens first. Fitness decides how likely you are to give, who's likely to give birth, and then you copy yourself into a random neighbor. So birth happens proportional to fitness, and then a neighbor is replaced. And so you follow the set of mutants. So the mutants, so there are some vertices that are mutants, some are residents, and so you have a set C, which is the vertices that are the mutants, and then all of the others are residents. And so there's a one-for-one swap in each case. So the population always stays at size n, the total number of vertices, and you just follow the set of vertices that are mutants until either you reach the empty set, so the mutants are eliminated, or you reach the full set where the residents are eliminated, and then that's the end of the process. And we're interested in what's called the fixation probability, the probability that given you start with a single random mutants, you end up at a full mutant population rather than a resident population. So here are some simple graphs. So these are the smallest possible graphs that have some that are not just two individuals. So two types of graphs with three individuals, two types of graph with four, and these are the potential states that you can move between. So states are identical if there's a one-for-one mapping from one to the other. There's only one. So for instance, in figure D, I've got a state that's got two black nodes and two white nodes, so two mutants and two residents, and there's only one with that. But of course, there are in that square, if you have that structure, there are four different ways that you could have those two mutants, but they're all equivalent to each other in terms of what can happen next, what fitnesses happen, what transitions happen, and so that's just written as a single graph. And so those are the different states. So if you've got three individuals or four individuals, your population follows a dynamic process running around between these states. So it starts at a random position, and a random position with one mutant, so one black individual and three white individuals, and eventually you end up either in a population with all residents or all mutants. So when you get to those end states, you then can't move away from them, because you always need one resident to replace a mutant or a mutant to replace a resident. So when there's only one type left, then the evolutionary process stops. And so the aim is to see what the fixation probability is, how it is affected by structure and various other different different factors like payoffs in games and so on, and indeed what particular type of game you've got. So one limitation of evolutionary graph theory, it's very useful and flexible, but all games are typically either pairwise or multiplayer, but in very specific ways. So you can define games such that I play a game against all of my neighbours, and then I'm involved in another game where I'm one of the neighbours of someone else. But then I'm always playing in a fixed number of players within a particular game. So real animal populations and so on will have different populations group sizes. So a lot of fitness will come from lone interactions, so not involving other players at all, pairwise, and any number, and in particular some variability in the number of individuals. Sometimes it's 2, sometimes it's 5 for the same individual. And so what we're going to discuss is a more general framework where there's more possibilities of how individuals interact, a natural way that multiplayer games come about. And then we'll think about this structure. Again, there's this structure that's going to be there, an underlying, so more flexible structure, but also then there's going to be dynamics on the top. There's going to be games on the top. And so we'll particularly be defining, I'm only going to talk about one particular multiplayer evolutionary game, but there are lots that are potentially considered. And I'll say a little bit more about some of the later ones right at the end. So the graph models that had those three components, graph, game, and dynamics, we've got the same kind of idea. But this time it's not a graph, it's a more complicated structure, but still the games can be very similar. The dynamics actually turn out to be rather similar as well. So here's the framework. This is what we've got. So we're going to assume a population of some number of individuals, capital N, and they can move to some number of places, capital M. So in some scenarios, we see that the N and M are the same thing, but in general, I've got N individuals and M places. And we're going to define a matrix which is N by M, and it just represents where individual IN is at any particular point. So a particular instance of this process indicates that If there's a 1 in that position, then IN is there. And if that individual N is the nth individual is there, and if there's a 0, it's not there. So every row would have precisely 1 individual. So of course, there's a simpler way of writing that, and just having a single vector which says individual 1 is at place 7, individual 2 is at place 3, and so on. So you just have a single string. But it's useful to be able to have this fuller matrix, just because underlying that are certain probabilities. And I want to be able to write down a probability distribution of where anyone is at any particular point. And that will naturally be n by m. And so the location matching that is a sensible way to consider it. It's sometimes we do consider the alternative formulation as well in a vector, but this is the formal I think logical place to start. And we'll consider probabilities of being at any particular point. So the property capital X is a little x, so a realization of our process. That can depend potentially on the whole history of the process. And so we consider what's the probability that our group has moved all of these different positions, conditional on, well, where we all started off, wherever the start position was, where we were next, then next, and so on. So our group could where we are now could depend upon all sorts of steps in the past. And there are essentially 2 different types of independence that we've considered, dependence or independence. One is to do with the past. So a history independent process is one where all our individuals just move. So we move now, and then next step, we're going to move again, and we don't notice where we were before. So we get up in the morning so we live somewhere, we get up in the morning, we move somewhere, we move to a particular place, and then we go back at night, and then we do it again. And where we go doesn't depend upon where we were before. So that's one potential set of independence. It can be that all of us move together in some way. So there might be some kind of herding or some kind of avoidance behavior. So there might be some correlation between where you and I go. And so that's even when there's history independence, there might be that. So an alternative is where we may depend upon the history. So it could be that I see where I was last. I even see where you were last, and that might affect me. But what's called row independence is where I essentially use all of the past information or some part of the past information to consider to affect my movement distribution. You do the same thing, but we then move independently of each other, conditional on the past. So I don't look at where you're going now. You don't look at where I'm going now. And so that's what we call row independence. And something that's both of those is just called independent. And that just means I've got a movement distribution, and so have you. And at every step, we just follow that independent distribution. So we'll look at something where, at some examples of the independent case, similarly at history independent but row dependent versions, and history dependent, row independent versions. And the history dependent version will be a Markov model where we just worry about where we were last. So this is an independent structure. So this is the standard realization. I've got individuals, and each of them have got a movement distribution over a certain number of places. And well, this representation is the general one for the independent model. So there are certain places, and I just have a distribution to go to these places. Some of them might not be able to reach. I might only be able to go to place 1 or 2, and you might only be able to go to places 2, 3, and 4. And we might not be able to, so we can't meet on 1 because you can't go there, and so on. But the standard representation is this bipartite graph. And so what happens is we move, and a certain number of individuals appear at a particular place, and then they play a game. What's the probability? So sometimes the payoff might depend upon all sorts of factors. It might depend not only on who's with me, but on the distribution over other places. But often we're only interested in what's the group at a particular place at a particular time. So who goes there? So if I want to work out what's the probability a particular group forms on a particular place, everyone's moving independently. So if there's the 6 individuals we're looking at, it just what the probability of that group forming there and no one else, it's just the probability that you go there, I go there, the other 4 guys go there, and all of the others go somewhere else. So just a product of probabilities of the P of going there, and then just 1 minus that. So they can go anywhere else. The only thing that matters is who's meeting there. And then we play a multiplayer game. And I'll show you an example of one of these multiplayer games. And then you just repeat this process, and our fitness is just an expectation of that over a large number of observations. So that's the way that works. So let's just look at a little example. So here I've got 4 places. One thing about having a very flexible framework is there are lots of things you can do, and so you can introduce tons of parameters all over the place. And so what we're mainly interested in is getting some method of controlling how individuals group or not without having multiple parameters. And so our choice of a single parameter to govern structure, obviously it's limiting in some senses, but it has a good way of either having bigger or smaller groups as you'd want, and greater and lesser mixing and so on, is picking what's called our home fidelity parameter. And with that, I just see all of the places that are next to me, and I guess I actually missed out the first line of this, which is rather important. And this is our territorial radar game, where every individual does have a home. So yeah, individual 1 lives at place 1, individual 2 lives at place 2, and they either, at every movement position, they either stay there or they go somewhere else. And so home fidelity decides how likely you are to stay at home. So I compare my home to a random neighboring position, and I'm H times more likely to stay at home than any of the neighboring positions. So if I've got 3 neighboring positions, my probability of staying at home is H over H plus 3. Similarly, if I've only got 1, it's H over H plus 1, and then I go to the other place with probability 1 over H plus 1. So if I've got more places to go there than another individual, each of them I'm less likely to visit than that other individual is to visit his 1 place, but I'm more likely to go somewhere else than that individual is, because I've got more choices. And so that's the way that works. So this little matrix here is not a transition matrix, because it's a each row identifies the probability of what every individual goes to over a particular place. So I'll go forwards to the next figure and then come back. So this is the set of places that graph that matrix represents. So I1 is the center of a well, it would be a star if I'd drawn the figure that way. I1 is connected to I2, I3, and I4, but all of the others are only connected through I1. So I1 stays, the individual I1 stays at home with probability H over H plus 3, and then it goes to each of the other places with probability 1 over H plus 3. The others, they just go either stay at home with probability H over H plus 1, or go to I with probability 1 over H plus 1. So that's that matrix that says the probabilities. And the representation that we had before of individuals to places is given in that figure B. So I1 can go to any of the places. I2 can only go to place 2 and place 1. So once we make our movements, how do we actually update the population? So we play these games. So I go somewhere, I play a 2-player game with you. Next time I'm on my own, and so I work out a fitness. How does the population update? Well, if you use the birth dynamics, then what happens is I'm selected for reproduction with property B, BI, based upon my own fitness is proportional to my fitness. So you look at all of the individuals and you just sum the fitnesses and then divide by that. So if you're fit, twice as fit as me, the probability that you're selected for birth is twice as much. There's one individual selected at each point, and then it will copy itself into a random neighbour. And what we mean by neighbour here, we don't really have a formal neighbour in the same sense. And so it's just the strength of your interaction with me. So we work out what's the probability that you and I meet. So we think about all of the different groups that we can meet. We can meet in, and then that's also weighted by how many individuals are in it. So if I'm picked for replacement to do the replacing, I will copy myself into a random neighbour. So if my group has got one individual in it, if I've got one other individual in it, then I definitely copy that one. If there are 6 other individuals, then everyone has got a probability 1/5 of being hit. So hence the scaling factor 1 over the modulus of G minus 1. And so and the overall weighting is just overall all of the different possible ways of those 2 individuals meeting. And so there's a strength of interaction of every pair within the population. And well, I'm not going to say too much about the different dynamics. There are 6 different dynamics that we use based upon whether birth happens first, death happens first, whether selection happens on the birth or the death. And there's also link dynamics where things happen at the same time. So a connection is picked, and then you interact across it. So there is a classic set of 6, which also are used in evolutionary graph theory, and we didn't need to adapt much. The weights are different things here, but the concepts are not different. And a little bit more in terms of the underlying things. Here's a game. So this is a particular multiplayer game. It's a multiplayer public goods game. So cooperators always pay. So I've got just cooperators and defectors. So cooperators always pay a cost, no matter whether they're on their own or who they're with. So this is quite a stringent one. Some of these games, cooperators only pay costs if they're with someone. Similarly, cooperators can't benefit from their own contribution. So this is what's called the charitable prisoner's dilemma, the underlying multiplayer process. But there are more other ones that are more generous to the cooperators. So we're trying to pick the one that's toughest for cooperation to happen. And each cooperator then produces a public good value V. So it pays a cost C, it produces a V, and then it shares it amongst everyone else, not itself. And so if you've got a certain number of cooperators, little a, and a certain number of defectors, then the payoffs are given as we have below. So some base payoff, you just have that no matter what. If you're on your own as a cooperator, you pay a cost C and get nothing back. If you're with some other number of individuals, then you share in the rewards from the other cooperators. Defectors do the same thing, but of course they do a bit better because in terms of the overall share, in terms of the number of cooperators, because they get a share of all the cooperators in the group, whereas the cooperator doesn't get a share of all the cooperators in the group because it doesn't get its own share. And so those are the payoffs for this particular game. Now, say there's a set of other games with very similar payoffs, and there's a multiplayer hawk dove game and all sorts of different other ones that you can define. So this figure. I don't say too much about this figure. This has got those 8 graphs that I had before as the underlying structures. It's not a graph as in terms of evolutionary graph theory. It's just a graph as the underlying structure where the individuals live. So the weights involved are different things to that particular graph, and so it's a different kind of structure. But this then shows with different values of reward. So that there's a fixed cost, a fixed baseline reward. I think the baseline R was 10. My cost was 1, and then the different values of the reward are as given. And then this is just the fixation probability of a single cooperator. So you throw in a single cooperator in the population of 3 or 4 individuals, and you see how well it does. And then you see how this varies with the home fidelity parameter. And in particular, when home fidelity is very large, all interactions happen. Basically, it's single individuals interacting almost all the time, and so you have a fixed fitness effectively, and so no matter what the rewards, all of these values converge to the same value. And in other situations, particularly when H is when H is 1, which gives them probably the most movement in most mixing, then there's a spread between the different values. But everything here, cooperators are doing badly. So if you can, the baseline comparison is against 1 over n. So 1 over 3 in the 3 individuals, 1 over 4 in the 4 individuals. Am I doing better than that? So if every individual was equally fit, I just picked a random individual to dominate the population eventually. What's that probability is 1 over 3, 1 over 4 in these cases, 1 over n in general. The baseline comparison, if I've got something that does well, it's got to be better than 1 over n, and that's what we're looking for. So the problem there is there's not sufficient mixing. So in a well-mixed population, the defectors win those kind of games before. It's like a standard prisoner's dilemma, because they benefit from the group without paying the cost. So the only way that cooperators can do well is if there's some kind of positive assortment. So cooperators are more likely to meet other cooperators. And so one way that you can possibly get this is by having subdivided populations. So I've got instead of just me living on a particular vertex, a set of individuals live on a vertex. And this work was in one of those papers with Karen Patney and in 2017. And this, so several things Diogo Pires, who's my current PhD student, is working on, and he's involved in this training grant, the European Union one. So here I've got a smaller number of places and individuals, and several individuals live on a particular place. I mean, in this simple little picture, just place 1 has got 2, place 2 has got 2, and place 3 has got 5. It's got 1 individual. But this is just a general. This is just a specific type of that general representation. So our general representation still follows some figure like B. So it's not. We haven't introduced anything different. What we've done is come up with this particular special case of that original formulation. So now we've got fixation probabilities, and I've got 2 dynamics now. I've got death, birth, death, and I've got death, birth, birth. And let me just talk a little bit about this figure. So there are 6 individuals in each case. If you look at the label on the bottom of the graph on the x-axis, then when there's a single 6, that means there's one place of 6 individuals live there. So they always go there because there's nowhere else to go. 6, 0 means there are 2 places, but 6 individuals live at one, and the other one is an empty place initially where individuals can visit. 6, 0, 0, there's 2 such empty places. 3, 3, there are 2 places, and 6 individuals, but 3 live on each. 3, 3, 0, there's a 3rd empty place, and so on. 2, 2, 2, there are 3 places with 3 pairs of individuals live as having them as their home place. And 6 ones is just that's the standard graph where 1 individual resides on each place. So in that first figure, that's where the selection happens on the first event. You can see that the cooperator fixations are all the solid lines at the bottom. The defector fixation are all the solid line, all the dashed lines at the top. That horizontal line is 1 over 6. So that's the baseline comparator. So if I beat 1 over 6, then I'm doing well. If I don't, I'm doing badly. And effectively, defectors invade populations of cooperators. Cooperators don't invade population of defectors. So it's not a very interesting figure because it tells you what happens in a well-mixed population. So nothing has changed. With the different dynamics, where death happens first, but selection happens on the second event, then that's very different. So death, birth, birth. And so if I've got effectively a well-mixed population, all 6 individuals start on 1 vertex, still exactly the same happens. Cooperators do badly, defectors do well. That's also true for the 6 ones together. But intermediately, where there's some kind of assortment, so the individuals live on certain places, then you can see that when there are 3, then there's a crossover. So when it was just 2 places and 3 on each, then the cooperators do well and the defectors do badly. When you've introduced some more spare spaces, actually, then that reverses again. We'd introduced these spare places because we thought that might help cooperation, but actually the spare places seem to make it do worse rather than better. The place where the cooperators do best is in these populations of size 2. So if I have a subpopulation of size 2, then my individuals primarily interact with their partner, and then occasionally interact with the others, but mainly with their own. And so what tends to happen, we've got, if you look at the parameter at the bottom, it's quite a big home fidelity parameter. So that means that you're mostly interacting with the other guy who lives there. So that gives a big positive assortment. And that's why this cooperator is so effective. And a small population, but non-zero, is good because it's enough that you can get the benefit from the other cooperator. But also, if you're thrown into a random population where there are defectors, you initially start off with a disadvantage. If one cooperator, 2 defectors, say, then the defectors do better. But you can triumph by good luck. And once you get into that population, that subpopulation is quite strong, and then it outcompetes other subpopulations. So you have an initial disadvantage, but that's outweighed by the subsequent advantage. And so this is it's just an example of this independent type model. And for the sake of time, I will skip the next figure, which says pretty much the same thing. So I'm now going to look at history independence. So this is a Markov movement model. So what happens is individuals, again, are moving about a similar kind of underlying graph structure, but instead of just making one movement and then going back again, what they do is they make several steps, and they try and assort in the appropriate way. So again, this is work that Igor and Diogo are working on. So individuals live on a graph, 1 at each vertex. Doesn't have to be 1 at each vertex, but that's what we've considered in each case. Each time step, they stay where they are or they move. There's a cost to move. If they move, they can't pick where they're going. They just move somewhere random, and then they see where they are. And so you look at where you are and decide whether you like it or not, and to a certain extent how likely you are to want to move or not. So you and I will have 2 properties. One is whether we're a cooperator or a defector. So that's my main type. But also, I've also got an overall what's called a staying propensity, which is how likely I am to move effectively from a lone place where I'm on my own. So sorry, staying propensity is how likely I am to stay. So if it's just me, the property of me staying where I am is this alpha, and if there are other individuals there, then I factor in who's there. And so don't worry too much about the details of this formula, but effectively there's a level of sensitivity. So S goes up and down, affects how much I pay attention of these other individuals. So if S is 1, I pay no attention to them at all. And if S is very small, then I pay a big attention to others. And so I just check whether there are cooperators or defectors there. I want to avoid defectors and mix with cooperators. And that's true whether I'm a cooperator or a defector. Defectors are no good to me if I'm a defector, or as a cooperator. Cooperators are useful in both cases. So both will try and mix with cooperators. And so there's an interaction process where you work out what the right staying propensity is for each different case. So a population will, so you'll consider all different defector population with different staying propensities, throw different values in, see what's the best one to defecting. Well, actually, you don't want to move around if they're all defectors because there's no gains and it'll just cost you. So they don't move much. Cooperators, on the other hand, they may well want to move to a certain extent, to mix with each other, but they don't want to move too much because they pay costs for each movement. And so the cooperators tend to have a different preferred version when they're in the dominant proportion in the population. And then you follow the process and see how it evolves. So I've got three figures here. One for the underlying, so three different underlying graph structures. One is, so this is the well-mixed population. The blue so on the vertical axis is the size of the population. On the horizontal axis is just how big the movement cost is. So 0, of course, it's free to move. 0.9, it's a pretty big cost actually. And so that there's a range between those. And on the complete graph, if the cost is pretty small, then our population favors cooperation. So blue means cooperators do better than 1 over n, and so you can actually see the stripe. So the figure on the right runs along the top row where there are 50 individuals, and so when the movement cost is low, you've got this blue region where the blue line is above the graph and the orange line is below the grey horizontal line. And then when you get beyond that, then both are below. So that means there's resistance to invasion from both times. So it favors, opposes change. So it favors stability. And that's what this grey region means. So blue favors cooperation, orange favors defection, grey favors stability. And in yellow favors change in both directions, though in this case there isn't any. So this complete graph really favors some kind of stability in general. Here is a circle, and there typically, at least when the population gets big, then either defectors do well or cooperators do well, and there's no in between where either they both invade the other or neither invades the other. So basically, once you get a big circle, then everything happens on a boundary in a similar kind of way. There's cooperators on one side, defectors on the other, and there's a relatively small group that are always interacting and I mean, it's okay. It's not quite like that, but there's not so much a frequency dependent effect in the same kind of way as in the other groups, because interactions only happen on a relative small number of places with a relatively small group sizes. Our third one is the star, and here we have this yellow region which favors change, and here this orange region which favors cooperation, so which favors defection. So defectors do very well on the star. Basically, it's very easy for them to reach cooperators. Because everyone has to move through the middle. And so if cooperators can find cooperators, often it'll be in the middle, and then defectors can hit them easily as well. But what often happens is there's instability in this kind of structure. So these different structures have very different properties, and there's a more general hypothesis on how the topology of the underlying structure affects the different fixation probabilities. So that's that version. As you'll notice by now, I'm tending to jumping around and talk a little bit about a number of different results, just because I want to talk about each of the different models rather than spending a whole talk on one specific one. So if I've got row independence, so now this model is not so much in the way of the dynamics. So here I'm just going to say how this process actually works. We have actually got some results on the dynamics now, but this is relatively recent. So this is work currently with a different PhD student called Hassan Haq, and Hassan is working on these correlated movement models. But up until a year ago, then there was nothing on this in terms of the dynamics, and still we're very much in a work in progress in this. So I'm just going to talk about how you can possibly get these correlated movement models. So in the fully independent model, individuals each follow their own distribution, and they don't pay any attention to the others. But in real animal populations, often there's some kind of herding behavior. So either you and I want to stay together, we're a group, or there's safety in numbers. or there's the dilution effects in against predators. So if you and I are together and a predator comes along, well, it may be it'll eat one of us, but if you're there, if I'm on my own, it'll eat me. But if you're there as well, maybe it'll eat you instead. So there's a benefit of having groups, but also we compete against each other for food or whatever. And so there are other benefits for not being in groups. So depending on the balance of these things, you may want to be with others, or you may definitely want to avoid others. And so what this model is trying to construct is a way of having a general flexible way of saying, okay, this is the overall distribution of locality that I want for my individuals, but I also want them to be able to separate out or group together based upon what the underlying requirement is. So the paper that this 2020 paper had these individuals we talked about the animal populations as such, but also it's useful for us to embed this in a more complicated structure. So just as a movement method to then work in these kind of evolutionary dynamics situations. So for the independent case, let's suppose my underlying movement distribution is PI. So every individual, let's suppose we're all starting at the same place, and every individual has got to, well, we're all starting with the same distribution. So every individual goes to place 1 with probability P1, 2 with probability P2, and so on. Then the probability 2 randomly selected individuals move together is the sum of PI squared. So probability that I'm together with the two of us together on place 1, plus together on place 2, plus together on place 3, and so on. So this is a general thing where you move independently. We coin the more general value T as a probability 2 individuals are together in general, and T is bounded between these two values. So if we've got this distribution, obviously we could potentially move together. So if both of us have this initial distribution, but we're always on the same place, then certainly we both fulfill that distribution because we move together with probability P1, move together with probability P2, but actually we're always together. So my T then would be 1 if we always move together. But if we move differently, if we move separately, we can't minimize our, I mean, you think, oh, the minimum probability of us being together would be 0 because I can go to place 1, you to place 2, or alternatively, we can flip over. And so we can have situations where we always stay apart. But that's not necessarily possible. So to fulfill the overall distribution. So there's a minimum value to fulfill a particular target distribution. And I'll just show one particular method of moving a group of individuals that can achieve everything within this range. So I can have maximum herding or minimum herding, based upon what I want. I mean, there are many different kinds of group distributions. So not just pairwise, three-wise, four-wise, and so on. And that requires something a little bit more sophisticated. But for this simple case, I can just use this method. So here's a wheel. So what I do is I allocate my base of my wheel with probability proportional to the overall, so with size of the segment of the wheel proportional to my probability. So if I've got 6 if I've got a probability of 0.4 that I want to go to place 1, then place 1's the length of the arc for place 1 will be 2 pi times 0.4, and so your region is just proportional to the probability of going there in your target. So then what I do is I spin my wheel, and then I've got my base, and I put a single. If I'm just following a single individual, I put it on a top wheel, and I spin it round randomly, and it will land in places following that distribution. But I could also put 2 individuals on that wheel, and each of them will have that individual distribution, and yet their position with each other relative to each other will be correlated. If there's an angle of 0 between them, so I1 and I2 have a spike that's on the same position. So if you're looking at this third wheel, the second wheel is the relative position of the individuals, and then you stick that on the top, spin it around, and if those individuals are very close together, they're very likely to be on the same place. If they're very far apart, they're very likely to be on different places. And indeed, to achieve maximum connectivity, maximum herding, you just put all the spikes on the same place. To achieve the minimum, you just have equal distance spikes. So if I've got n individuals, then the angle is just 2 pi over n by the individuals, and then you stick them on the top, and then you have a maximum dispersion between the individuals. And so there's a very straightforward way of doing that. And then, so I mean, there are all sorts of different ways you can do it, but that's the natural simplest way. And so you just change your angle, and you can increase or decrease herding as you see fit. Here's a figure. So on this figure, should I be shutting up now?
It depends how much time you want to leave for questions.
When do we stop?
Normally we stop at 12, but since we had some technical problems, I suggest that you go until 12. And for those who would like to stay for a few questions, we can accommodate this. Okay, perfect. Right. So I won't say too much about these figures then, because I've got one other thing that I want to talk about. But effectively, this gives you a distribution of the locality of our population. So the top right figure just indicates either everyone is on place 1, everyone is on place 2, or place 3, or occasionally, along the boundaries, you've got individuals that are just between place 1 and 2, but not. So there aren't many that are on places 1, 2. There aren't many situations where there are individuals on place 1, 2, and 3. This is when you've got a tight population. The other figures, you've got these spreads within the population, within the triangle. This indicates that often individuals are not all on one place, and so a position in the middle of the triangle indicates a distribution where a population. And how many individuals were there here? There are 10 individuals. And so your population, some individuals are on one place, some individuals are on another. So I'll skip that just because of time. One last thing I wanted to talk about. We also have done some work on general variable group size, and we're doing this now also with evolutionary process, with a fully dynamic process. But this is going back to the classic evolutionary models, and so this is just considering how a variable population size works. And what the effect of varying population size can be. So we consider a population where you pick a random. So you've got well-mixed population, infinite population, and you just pick a random group of that from that population, and the distribution of the group size you pick follows a negative binomial distribution with a given mean group size, but then varying values of a dispersal parameter S. So S relates effectively it relates the variance to the mean. So a big S meant you had a low variance. A small S was a large variance. I haven't put the details up here. And so how does that affect your population? And so the plots you're going to see are plots of the payoff to a cooperator in such a population minus the payoff to a defector. So an incentive function. Would I rather be a cooperator or a defector? And so these are just the plots. So the solid line is S is 1. The dashed line is S follows is equal to mu, and then the dotted line is the maximum value of S, which is the minimum variance. And so the main plot of this is that for these particular types of graphs, particular types of games, then the solid line dominates the dashed line, dominates the dotted line. This doesn't happen for all games, but for these particular games it does. And what that means is variability is unambiguously better for given mean group size, given parameters, given payoff parameters, is unambiguously better for cooperators than less variability, because that line completely dominates the other. So, for instance, if you look at the third figure along, you can see that for all values so the incentive function is on the y-axis. 0 is halfway up, and so if you're above 0, then you're doing better. And so if you're above 0 for
for when the value is 1, then 1 is stable. So everyone cooperating is stable. If you're below 0 for when the value is 0, then everyone defecting is stable. And so here, the cooperators do better than defectors for S is 1 for all population sizes. So all cooperators is best. For the dash to the dotted line, that line is below the axis for everyone. So all defectors is best. For the dashed line, then for a small number of, when there are a few cooperators, defectors do better. No, when there are a few cooperators do better. When there are few defectors do better. So there's a stable equilibrium. So a line going downwards, crossing the axis, stable equilibrium at that point. And so then there's a mixture for that intermediate value. And you can, for different games, you've got different patterns. So the next game, there's the fourth, the row 2. So row 2, column 1. Then you've got unstable equilibria, where there are 2 optima. So that was basically the text that I said in a quick way. We've got to the point, so I won't say much more. So that's the framework we've developed. There's these 3 main components: structure, game, dynamics, and game. And we've applied it in a number of different areas, number of different models used. And obviously, it's still very much under development. Still, we're looking at some of the core theory. There's a lot to develop. We looked at a number of different models here: fully independent models, history dependence, row dependence, variable group size, and this is ongoing work with say Igor, with Diogo, with Hassan in particular, and that's where I'll stop.